Hi everyone, welcome back. In this video, we will discuss spontaneous reactions, the entropy of the universe always increasing for those types of processes that are spontaneous, as well as Gibbs Free Energy. Okay, so for a spontaneous reaction, we learned from the second law of thermodynamics that the entropy of the universe increases. And so delta S of the universe is greater than 0 for a spontaneous process. And in this case here, we're talking mainly about reactions because we're studying chemistry together. But same goes for like any processes that are considered spontaneous. So in addition, when we're thinking about the entropy of the universe, we need to take into account that the entropy of the universe is equal to the entropy of the system plus the entropy of the surroundings. So we have to think of the system and the surroundings when we think of the entire universe. All right, so let's think about an exothermic process, something you would have studied in first semester general chemistry, maybe be more familiar with. An exothermic process means that the enthalpy is negative, heat energy is released, and so it's released from, if we're thinking about the reaction as the system, heat energy for that exothermic reaction is released from the system to the surroundings. So the entropy of the surroundings should increase. But for an endothermic reaction, we understand that heat energy is absorbed, so you have a positive enthalpy, and so it's taking in energy from the surroundings, and therefore the entropy decreases. And the entropy of the surroundings decreases. Now we can solve for the relationship of the change in entropy of the surroundings with the enthalpy of the system. So this here, we're referring mainly to the system and how the system is affecting the surroundings. And basically the formula for you to learn is that the change in entropy of the surroundings is equal to the negative enthalpy of the system over T, as long as we're working at constant pressure and temperature. And this negative sign here that we see for this formula, the negative sign reflects that according to the first law of thermodynamics, any heat leaving the system must go to the surroundings and vice versa. So here is basically representing the first law of thermodynamics, that energy cannot be created nor destroyed. And so any heat that's lost from the system must go straight to the surroundings, or vice versa. You could have the negative here, right, where the system needs heat energy, so the surroundings loses it. But they're equal and opposite to one another. So there's a relationship between surroundings and the system, and we see that as well in the case of entropy. We can understand that if our reaction is, for example, losing heat, It's an exothermic process, then there's more disorder, there's more of that energy being dispersed in the surroundings, so you have greater entropy. Whereas if our system needs some energy, it's taking that from the surroundings, and so that's why there's a decrease of entropy in the surroundings. So there's definitely a relationship between enthalpy of the system and entropy of the surroundings. So let's work a problem together. Like, how does this come into play? Because in the end, we're more concerned about the entropy of the universe, right? If the entropy of the universe increases, then we can confidently say we have a spontaneous reaction. Like, that's our goal here. All right, so let's look at the combustion of propane gas. So we burn propane gas in the presence of oxygen to get carbon dioxide and water. All combustion reactions, we were burning in the presence of oxygen. Products are carbon dioxide and water. And it's highly exothermic. If you've cooked with the gas grill, you know that helps you to cook your food. The enthalpy for this reaction is a negative 2044 kilojoules per mole. Now the first question is asking us to calculate the entropy of surroundings at temperatures equal to 25 degrees Celsius. So we're going to work in Kelvin when we're dealing with thermodynamics. So first convert Celsius to Kelvin by adding 273. So this is 298 Kelvin. And we just learned the formula for calculating the entropy of the surroundings. It's equal to negative enthalpy of the system over temperature in Kelvin. Now, just something to make note of that may not be apparent right away, but the reaction is your system. We have to think from the perspective of a chemist, and as a chemist, we are greatly concerned with our reactions, right? So that's why we always focus on them as our systems. Everything else around it is the surroundings. So it's just very important to make note of that. So that's why I will plug that number in here. So negative, and then this is actually negative 2044 kilojoules per mole divided by 298 Kelvin. A lot of times the units, and I've discussed this in a previous video, the units will be in joules per Kelvin, and it's assumed per mole of the reaction. You could also write per mole as well. So you'll see it kind of both ways with the units, that sometimes moles is dropped. But if it is dropped, then you know it's per mole of that reaction. All right, when you plug this into your calculator, you should get 6.86 kilojoules per Kelvin. And that is equal to a positive 6.86 times 10 to the third joules per Kelvin, if we wanted to report it in joules per Kelvin, which is typically how entropy is reported. And so you have to ask yourself, does this make sense, right? Always try to rationalize our answers based on our understanding of the science. So for example, we have a very exothermic process. That means our reactions releasing a lot of heat energy to the surroundings. So should we expect a positive entropy of surroundings? Yes, we should. We just talked about that trend on the previous slide, that for exothermic processes, that the entropy of the surroundings should be increasing. So therefore, a positive value totally makes sense. Now, the next question is asking us to determine the sign for the entropy of the system. So to do this, I will eventually teach you how to calculate the change in entropy of a reaction, basically products minus reactants. But I just want to know the sign in this question here. So quick and easy, just look at the moles of reactants versus products. And so it looks like we have 6 moles of reactants. And then that produces 7 moles of, and I should say gas reactants, and 7 moles of gas products here. And I got that from the stoichiometric coefficient. So 1 plus 5 is 6, 3 plus 4 is 7. So the fact that we are going from 6 moles to 7, it means we have more disorder on the right side of the arrow. So the entropy of the system is also positive, would have a positive sign without even knowing like exactly what the value is. We know it's positive. So in order to determine the sign for the entropy of the universe, we know that's entropy of the system plus entropy of the surroundings. And if you have a positive plus a positive, you will have overall a positive entropy of the universe, which means that the reaction is spontaneous. Because we have a positive entropy of the universe. This follows the second law of thermodynamics. And so it's a lot of work to kind of determine if something's spontaneous or not. We'll have an easier way to determine it in a second. But why it's useful to know if you have a spontaneous reaction is that when you're designing a reaction in the laboratory, there's a lot of money that goes into buying the reactants. There's a lot of time and like money spent for the scientists to run the reactions. So it's really important for us to fully understand the kinetics as well as the thermodynamics. That's what we're focusing on here in this chapter of our reactions, so that if we need to make changes, we can. So later on in this series of videos on thermodynamics, I'll go over ways to help a non-spontaneous reaction become more spontaneous. So it just, you never want to step in the lab and just try to run a non-spontaneous reaction and not do anything to help it out, right? That's just a waste of time and waste of ingredients. So that's the reason why we're spending a lot of time on trying to understand the thermodynamics for these reactions. But there is another way to determine if a reaction is spontaneous or not, and that's to use what's called Gibbs Free Energy. So what's really nice about Gibbs Free Energy is that it focuses entirely on the system. And in our case, from a chemist point of view, it's the reaction, right? That's something that we can control, like to the best of our ability and what we're really interested in here. So the change in free energy and we will represent that as delta G of a chemical reaction represents the maximum amount of energy available or free to do work after accounting for the heat lost to the surroundings. Due to the second law of thermodynamics. Remember in the first video I had discussed how nature has a heat tax, right? Every single energy transaction doesn't occur at maximum efficiency there's always that heat loss to the surroundings, and then that helps to increase the entropy of the universe, right? So a lot of times students are like, well, I thought energy wasn't created nor destroyed, so how can it be free? And I just want to clarify that that term free just stands for the maximum amount of energy available to do work, after accounting for the heat loss of the surroundings. So it's not free at all. It's just what the energy that's left over after nature has taken its heat tax out. All right, so let's derive the formula for Gibbs Free Energy that you will need to know to solve for it. So we learned that the entropy of the universe is equal to the entropy of the system plus the entropy of the surroundings, but that the entropy of the surroundings can be also referred to as negative enthalpy of the system over temperature. So that was the formula that we used right here. So basically I substituted that in for entropy of the surroundings, because I'm trying to get everything into terms of the system. I'm going to multiply everything by negative t. So negative t, actually, I think I'm going to write it over here. So negative t delta S of the universe equals delta S of the system. Actually, let me fix that real quick. Negative t delta S of the system plus delta H, enthalpy of the system. So right now I've multiplied this equation by a negative t. So I got negative t delta S, or entropy of the universe, is equal to a negative t times entropy of the system plus, because I multiplied it by negative t, plus the enthalpy of the system. So this turns into Gibbs free energy is proportional to the entropy of the universe as a function of temperature. And so therefore this is actually delta G. And this represents the Gibbs free energy of the system is equal to delta H of the system minus T delta S. And you would probably see it more as delta G is equal to delta H minus T delta S without having to write system on there. But I just want to emphasize here, the really neat thing about Gibbs free energy is it focuses on the system only, whereas you saw in the previous problem that we had to take into account the entropy of the surroundings and the entropy of the system to even think about the entropy of the universe. Okay? And so once we are able to solve for delta G, and definitely know that formula, that's going to be used quite often in this chapter, then the trend is, how that helps us is that if we end up with a negative delta G, then our reaction is spontaneous. And if we end up with a positive delta G, then our reaction is non-spontaneous. So it's good to know that relationship there. All right, something that's also really important here is to understand that it's not just about being positive or negative delta G's, but that temperature plays a role as well. So I wanted to do, this table here has an abundance of information in it. It may seem small, but it's mighty. And I wanted to go through it with you. And I don't think it's very wise to try to memorize it, because that can be quite confusing. Like if you're on an assessment and you get confused, you want to make sure you can derive these sorts of relationships. I'm going to show you how to do that algebraically, and I didn't leave a whole lot of space, so I'm going to have to do it and then erase it and do it again for each scenario. Okay, so I'm a very math person, so I like I said, I like to use these equations to help me out here. So I'm going to use delta G is equal to delta H minus T delta S, and I want to check out the first scenario. What happens if delta H is negative and delta S is positive? Then I have a delta G is equal to a negative minus temperature, so T, times a positive value, right? And so therefore, this negative minus this positive will always be negative, regardless of the temperature. Okay, so if you have a negative delta H and a positive delta S, because you're subtracting that positive out there, then delta G will always be negative. Negative minus positive is always negative. And therefore, under these conditions, the reaction is spontaneous at all temperatures. It doesn't change because delta G will always be less than 0. So it'll be spontaneous. Let's check out the next scenario. What happens if enthalpy is positive and entropy is negative? So I just like to plug in signs there. I have a positive here minus a negative, and you can say, I guess I should put the T in there, minus T times a negative value. Well, this negative times a negative here basically is a positive here. And so therefore, positive and a positive, we will always have a positive delta G, always. And so it doesn't matter what temperature we have here. If we have a positive enthalpy and a negative entropy, we will always have a positive Gibbs free energy, which means that this type of reaction is non-spontaneous at all temperatures, low and high. All right, so what happens if we have a negative enthalpy and a negative entropy? So delta G is equal to a negative minus T times a negative. Okay. So the fact that enthalpy is a negative, that's favorable, but we know that this term here, a negative times a negative, basically is a positive. So for delta G to be negative, we want the enthalpy to be much greater than this term here, this T delta S, right? We want this to kind of overcompensate what this may be bringing to the non-spontaneity, right? It's making it more positive. And so, based on these conditions, if we're at low temperatures, if this number is really small, that makes T delta S very insignificant. And then enthalpy wins. It's like the dominant factor here, and it's negative. So this type of reaction is spontaneous at low temperatures. The low temperatures need it to kind of make T delta S insignificant. Because remember, negative times a negative, this would be positive. We do not want that to dominate over the enthalpy that's negative. But if our temperature is really high, if this number is really big, then now this particular, term here, T delta S, could dominate the enthalpy. That positive could overcome the negative. And so at high temperatures, this reaction would be non-spontaneous. And then the last scenario, if, let's say, we have a positive enthalpy and also a positive entropy. So this would be a negative term here, because it's just like negative times a positive, negative here, and this is positive. So enthalpy, not favorable, right? So we want this term to be big so that that negative can dominate that positive. So in this case here, this reaction is spontaneous at high temperatures. Like, make this number huge so that it can dominate that not so favorable enthalpy, that's positive. But if this is a small number, if we have very low temperatures, then this would be a non-spontaneous process, because then the enthalpy would dominate and then it would be positive. So in that case there, Gibbs free energy would be greater than 0, non-spontaneous reaction. So I know that's a lot to take in, and in my years of teaching students, this can be a little bit confusing at first, and I get it. So try to kind of talk yourself through it again, kind of like how I discussed it with you. You know, I really suggest that you use math to kind of derive these relationships rather than trying to memorize the negative, positive, and then spontaneous or not. You know, it's important that you can use the Gibbs free energy equation and the signs of enthalpy and entropy to derive and predict what the sign of Gibbs free energy would be. Once you know that, then you know if it's spontaneous or not. Okay? Just my word of advice there. So let's go ahead and let's calculate the Gibbs free energy of a reaction and predict whether it's spontaneous or not. And I should write here, this is Gibbs free energy at standard conditions. I'll discuss that in a future video, but anytime you see the degree sign there, it just means standard conditions. So the hardest thing here, to be quite honest, is just to make sure your units are in the correct form here. So usually Gibbs free energies will be given in kilojoules. So I'm going to keep my enthalpy in kilojoules. But I noticed that my entropy is in joules per Kelvin. So I need to convert entropy into kilojoules. And so I just need to divide by 1,000. So the entropy of the reaction is equal to negative 0.157 kilojoules per Kelvin. Temperature's already in Kelvin, so we're good. So Gibbs free energy under standard conditions for this reaction is equal to delta H minus T delta S. So negative 95 kilojoules minus 298 Kelvin times a negative 0.157 kilojoules per Kelvin, T delta S. And you would get negative 48 kilojoules. And like I said before, sometimes you'll see it written as kilojoules per mole. If the mole is not written there, don't worry. But it is assumed that this is per mole of reaction here. So we have an answer for this particular reaction given these conditions for enthalpy, entropy, and temperature. Our Gibbs free energy is negative 48 kilojoules. So what does that tell you about the reaction? Is it spontaneous or non-spontaneous? Fantastic. It is a spontaneous reaction because we have that negative 48 kilojoules. That negative sign tells us it's indeed spontaneous. So just in summary here, you can determine if a reaction or process is spontaneous through using Gibbs free energy. Delta G is equal to delta H minus T delta S. Or you can also use determine spontaneity by the entropy of the universe, right? But then you need to figure out what's the entropy of the system, or at least the sign, and then entropy of the surroundings to figure out if it will be spontaneous or not. And just remember as well that Gibbs free energy is the maximum amount of energy available to do work after nature has taken its heat tax. And so we're accounting for the heat loss to the surroundings. And then something, as I've suggested for you to do, is kind of walk yourself again through this table. Try to derive it yourself, or figure out a way to remember these relationships and be able to derive them for a future assessment. And then from here on out, we're going to be doing a lot of kind of problem solving here. And so a key equation to remember is delta G is equal to delta H minus T delta S. The most challenging part I've seen students struggle with thermodynamic calculations is just making sure that they're in the appropriate units. Sometimes students forget to do those kind of unit conversions, and then unfortunately they get the wrong answer. So don't fall into that trap. All right. Thank you all for watching, and I'll see you next time.